Okay, so in the last video, we looked at how we could store a quantity in using the stepping action. And in that case, we looked at the mean kinetic energy of electrons which are created as secondaries. And we spat it out at the end of our run. And we also stored how many electrons, secondary electrons were created. And that was all well and good. We created a variable first in the stepping action header, and then we initialize it in the constructor where the stepping action is created, and then during each step, so every time a particle is updated on the track, then we called this if statement to decide whether the particle was a secondary electron, and if it was, for the very first step, we would get its pre-kinetic energy, and using that we were able to get the mean. So that was all well and good, but if we wanted to determine the spectrum of electrons created, then this method doesn't really help us much because it's just the mean quantity. Whereas if we wanted the actual spectrum, then we'd have to create an array and then have some logic of where to store the quantity in the array. But a bit of a simpler method is just to use root. And in this case, if we open the run action class, then we're using the Geant4 analysis. Don't need that. The Geant4 analysis manager, which has root functionality built in. Now, just as a disclaimer, I would never use the built-in Geant4 analysis manager since it's slightly restrictive, but for our cases, it serves plenty of usability, and the methods to implement it is much more simpler than if we were just used root from scratch without using the G4 root class, which simplifies the techniques a bit, but strips away a bit of the power. But don't worry about that. So using the Geant4 root analysis, we can create a header. We can create a histogram. So just bind energy of results. So where we do that is in the run action constructor. So if we want to make a histogram, all we need to do is go analysis manager, and then we access the h1 function, and then we give it a name and then a description. So let's call this secondary electrons, and then we give it a range. Then we give it number of bins. So let's just give it 100 bins in this histogram. Then we give it a minimum, and let's go 0. And let's store this. So we've got we have a 1 MeV primary electron. So let's just have a maximum histogram set to 1. And that's all we need to do to create it. So just go over this thing. So what this function is doing is it's creating a 1D histogram, and we've given a name of H1, and we've given a description of secondary electrons. It has 100 bins. It's got a minimum quantity of 0 and a maximum of 1. Then from that, if we go to the stepping action, the stepping action over here, then if I already got it in here, just looking. So if we create an analysis manager core, I think we've got it here. Okay, we've got the header. Sorry. So we got G4 root included. So all we need to do is create an instance of the analysis manager, Geant4 analysis manager. So we just do with this auto and analysis manager, and we go G4 analysis manager, and we go instance, and if I spell that right, then after that we can go analysis manager, and we can go fill h1, and I'll just describe what this is actually doing shortly. So go fill h1, and then we go 0. Then we'll just give it the pre-KE. So what this code's doing, it's pretty much all this does is it creates an instance of the G4 analysis manager class, and we'll do that with the header. And so what this does is this gives the stepping action class access to the functions in the analysis manager. So we've got the access to the analysis manager class and all the functions, and in this case we've got them all defined in the run action. I'll just get rid of some of these ones that are open too many times. Get rid of physics list while I add it. So this instance of the analysis manager gives us access to all the Geant4 analysis functionality, and then this analysis manager here, it's access the fill h1 function. So in the run action, we were using the create h1 function before, and now we're using the fill h1 function here. And then the first the first argument of this function is the histogram ID, and this ID is based on the order. This is based on the order of when the histogram is created. So because this is the first histogram created, it automatically has a value set to 0. And if I created another 1D histogram, it would have an ID of 1. And there's a way you can access it based on the name. So instead of using the ID, we could also use the h1, but I'll just show that in the notes perhaps, and won't worry about here. So all it's doing is fill in the h1 histogram pretty much. So this has an ID of 0, so fill this histogram with this quantity of pre-KE. So one very important thing to do is to specify the units. So before, when we were storing it here, we were when we were storing the pre-KE to the mean KE, we didn't specify the MEV, and that's because this mean KE electron, we defined it as a Geant4 double, and so in that case, this mean KE variable, it knows what unit it is because it's part of the G4 units, and so it can keep track of whatever quantity is stored in it. So if we had a KEV value stored in it, it would know to update it or change the units to whatever the built-in units or whatever. So it doesn't matter there. But whereas with root, it isn't part of Geant4 itself. We're just adding functionality from a separate program. And so they don't use the Geant4 units. They just use normal doubles, like normal variables, so they don't have energy and stuff. So we have to specify the units of this actual quantity, and that'll convert it. So if we compile that, and maybe it'll work. Okay, so let's just quickly run that with 100 electrons with 100 MeV. I think, yep, 100 with 1 MeV, yep. So number of electrons created was 330, and let's just go lstr to check. So we got a root file called basic output, and this name is based on the name we give it in the run action. So here we give it a name of basic output. So if we just quickly wanted to check the contents of this root file, so we see it was 32 kilobytes, so we can just launch root with -L, and that will avoid opening. So if you don't use -L, you'll get a splash screen, so an animation. Actually, let's just do it now. If I leave this -L, you'll get this loading screen of root 5, and it takes quite a long time to load. So when you're off campus, it takes a lot longer. So the -L is just for the logo, stands for logo. So put open root with -L, and it will stop the logo from launching. So once you launch root, you can just open a UT browser. And again, if you're off campus, it might take a bit of time. Okay, it wasn't too bad. So if we just make it a bit bigger, we can, you see we've got this navigator here. So if we go to basic output, and then just go to this H1, then we see got a mean of 6017. So let's just go to our stepping action output. So 6017. And we've got 330 entries, so our two quantities are lining up nicely. And let's just change this to a log viewer quickly. Y. So you see most of our electrons are about, like the most frequent is, let's just zoom in on the scale. And we're pushing our connection. Okay, so most of the electrons are created with an energy of less 0.01 MeV. So that's all good. So again, we've got agreement between our stepping action output and what we just stored with our root histogram. So just to recap what we did. So in the last video, we just stored the mean quantity just using a single variable in the stepping action. But now this time we used root, which has histogram functionality built in, and this allows us to store spectrums of particles much more easier, and gives us some built-in functionality. And in the next video, I'll just show an example macro of how we can plot this data, and as well as extract this data to a text file, since not many people like using root straight away.